Hello everyone, and welcome to this semester's General Chemistry course. My name is Hannah, and I'm your professor for the chemistry course this semester. Before we begin our lesson, I would like to show you the contents of today's presentation. So first, I will discuss about the course contents and what to expect from this class. And then we will move on to the introduction of chemistry. Some of you probably have a background in chemistry from your senior high school, but maybe some don't have it or some forgot it. But don't worry, because today is our first day. I will be guiding you throughout the basic concepts of chemistry. And we will first go at a comfortable pace and build up from there to study the next lessons. So today we will cover the atomic theory, a brief history of the discovery of atom, and the notable philosophers and scientists who proved its existence. And we will also give an overview of the periodic table and the elements, the discovery of pure substances and elements. And what happens when elements are combined together? We will have compounds. And what is an element made of? So the building block of matter. And lastly, the summary of the key points. Course outline. So this is general chemistry. It is a 3-credit course and it has no prerequisite. So these are the lesson summary of the outlines of the lessons. But please take a look at the syllabus provided by our department to check more details about it. Because this is not like one topic per week, because some topics are easy. Like today, we will cover the first 3 lessons, but some lessons are more advanced. Like for example, chemical bonding and molecular structure. We will have some calculations and familiarization with naming compounds. So please check the syllabus and also the academic calendar, because we will have our midterm examinations and final exams based on the schedule in the academic calendar. And I think now you are ready. What is chemistry? So when people hear the word chemistry, they immediately think or imagine something like this. A person mixing some chemicals inside a lab. Or something like this. Some complicated chemical equations that are difficult to understand. But in reality, chemistry is all around us. So it's in the food we eat or the air we breathe. It's everywhere. So by book definition, chemistry is the study of matter and the changes it undergoes. And as a recall, maybe we remember what matter is. Matter is anything that occupies space and has mass. So it means that anything that we see, anything that we can touch, even those things that we don't see, such as air, is called matter. So how chemistry shapes the world around us? Let's take a look at the practical applications of chemistry. One major example is in medicine. So scientists are able to develop medicines that can cure our diseases because of chemistry. And they can also develop vaccines because of that. So our doctors and other scientists study the chemical structure of the viruses, such as the COVID-19, that train the body so that they can develop vaccines that can train the body to fight viruses and prevent the outbreak, like what happened several years ago. So through chemistry, space travel became possible. So NASA uses liquid hydrogen and liquid oxygen as rocket fuel. And maybe you are familiar with the famous Moxie experiment on Mars that turned carbon dioxide from Mars' atmosphere into oxygen. And To give examples of more relatable applications, I'd like to say that we actually do chemistry on a daily basis. For example, chemistry in cooking or baking. So when we bake a cake, every ingredient plays a specific role, and chemical reactions transform the raw dough or the mixture of all the ingredients that we have into soft and flavorful cakes. And even though some people don't study chemistry, they probably know that baking soda is needed so that the cake will become fluffy. And also in the things that we use daily, like our clothes. These are products of some chemical reactions using some polymers. So it's also a product of chemistry. So now we are ready to know the basics. But to understand what we know today, we first need to understand how it all started. So on the following slides, I want to show you a brief history of the building block of matter. And of course, we should give credits to the philosophers and scientists who first studied all these things and shared it to the world. So around 400 BCE, a Greek philosopher named Democritus proposed that all matter consists of a very small indivisible particles named atomos. So atomos is the Greek word for indivisible or uncuttable. So according to him, if we zoom into any matter, a matter has a very, very small indivisible unit that cannot be broken down But another scientist, also a Greek philosopher named Aristotle, disagrees with the concept of atoms. So according to Aristotle, matter is continuous and infinitely divisible. Like if you cut something like this apple into half and cut it to half again and do the process over and over, we will just end up with a smaller version of what we cut. According to him, there is no end to smallness, unlike the idea of Democritus that there is a very tiny component of a matter that cannot be broken down anymore. So, according to Aristotle instead, that matter is composed of 4 fundamental elements, namely earth, water, air, and fire. During that time, Aristotle is more famous than Democritus. So for over 1,000 years, the people in the Western world believe his theory. His theory that everything is cuttable and there is no end to smallness. And now, let's fast forward to several hundreds of years, around the 8th century. So an Arabic alchemist named Jabir, also known by the Latin name Geber, who developed purification technique to purify substances and synthesize new compounds. Although he did not study about atoms, his experiments helped the next generations of scientists to discover it. So one example of his developed techniques is the distillation. So it's a process of separating and purifying liquids by heating, vaporizing, and condensing them. So as we go on to our lessons, we will know more about these techniques, but it will be on the next lessons. This is just an example. And following his steps, other scientists developed this process called fermentation that also leads to the purification of substances. Like if we ferment fruits, it's not just fruit, but we can divide its components into pure substances such as water, acetic acid, alcohol, and sugar. So a substance is a form of matter with constant chemical compositions and characteristic properties. Like for example, this water. It's a uniform solution, so it's considered a substance. Also this acetic acid. and sugar. So it's not a mixture, but pure substance. Pure. But later on, we will know whether it's really pure or not. But after hundreds of years, a French couple named Antoine and Marie-Anne Lavoisier followed the steps of the earlier scientists and discovered that certain pure substances can further be divided into simpler components through chemical reactions. So let's take water, for example. If we boil water, it will turn into steam. It is still water, but in a gas state. So the Lavoisiers discovered that steam can further be purified into two separate gases, the hydrogen and the oxygen. But they tried their best to separate the hydrogen and oxygen even more, and no matter what they do, it stays as hydrogen and oxygen, so it cannot be broken down into another thing anymore. So they call them elements. So an element is a pure substance that cannot be broken down into simpler substance by chemical means. And from that moment, scientists around the world started looking for pure elements, and they started organizing elements based on patterns in their properties that resulted to this table called the periodic table of elements. So the periodic table helps scientists predict element behavior, and we will further discuss it on the next lesson. So today is just an overview. So elements exist in different states at different conditions. So here I want to give you some examples of elements at room temperature. So elemental carbon, gold, and sodium exist as solid in liquid at room temperature, while mercury and bromine exist as liquid, and hydrogen, oxygen, and chlorine exist as gas. So we can combine two or more elements to make a compound, and the resulting compound could take different form or state depending on the conditions such as temperature or pressure. So here are some examples. Under the right conditions, the elements sodium and chlorine can form sodium chloride, and hydrogen and oxygen can form water. So now it's time for a review of concepts. I have a little activity for you, so please try your best to answer it. Which of the following diagrams represent elements and which represent compounds? Each color sphere or truncated sphere represents an atom, so it's already a clue. Each color is an atom, and different colored atoms indicate different elements. So what is letter A? Is letter A an element or a compound? Compound. I think it's pretty obvious because there are purple sphere and some gray sphere. So of course it's a compound. And letter B, I think is very easy. Same sphere, same color, same size. Element. What about letter C? Compound. And letter D? Element. Because even though they are lumped together, they are composed, these truncated spheres are composed of the same atom. So it's still an element. And now let's go back to our timeline. and move on to the very first scientific evidence of the existence of atoms. So around 19th century, a chemist and school teacher in England named John Dalton discovered that in a chemical reaction, elements always combine in fixed ratios to form certain compounds. So for example, we want to produce pure carbon monoxide. We should always add 1 gram of carbon and 1.33 grams of oxygen to produce pure carbon monoxide. Because, for example, we have 1 gram of carbon and add 2.66 grams of oxygen, it is pure carbon dioxide. And for example, we have 2 grams of carbon and we want to produce a pure carbon monoxide. Then, we need 2.66 grams of oxygen. So he was thinking, why is it like this? So he concluded that if different elements behave differently, then there must be something within them that causes this. He then proposed that elements are composed of extremely small particles called atoms. So he named them atoms following the Greek word atomos because he thought that these particles are indivisible, just like what Democritus proposed. So in his theory, different elements are composed of differently sized atoms, and atoms within the same elements are similarly sized and shaped, just like these examples on the screen. And he proposed the law of multiple proportion that states that in any compound, the ratio of the numbers of atoms of any two of the elements present is either an integer or a simple fraction, just like what I discussed a while ago. So now let's have a review of concept again. So the atoms of elements A, represented by blue sphere, and B, represented by orange, form two compounds shown here. Do these compounds obey the law of multiple proportions? The answer is no, because there is an excess of atom of element B, orange. So according to the law of multiple proportion, it should be always the same ratio. So if you have another one of the blue, you should only have two of the orange, but it has an excess. But the word atom means indivisible or uncuttable. Are atoms really indivisible? The short answer is no. So research conducted in the 1850s into the 20th century provided clear evidence that atoms have internal structure and consist of smaller components known as subatomic particles. So it consists of a nucleus, which is at the very core of the element, and the nucleus is composed of an uncharged particle named neutron and a positively charged positron. And also, for each of the positively charged positron, a negatively charged electron is attracted. So if an element has 3 protons, then it also has 3 electrons. But we will discuss more about this on the next lesson. So this is an overview of our next class. So we will discuss about subatomic particles, including the nucleus, proton, neutron, and electron. And we will also discuss about the atomic numbers, mass number, and isotopes. And also, we will discuss the periodic table in detail. So we will discuss the trends and how the periodic table is organized and what do the numbers that you see here. I will give you a more detailed periodic table next week. So, and we will study the numbers. What do those mean? And we will also move on to studying chemical bonds. We will know what are ionic and covalent bonds and Lewis structure, and we will be naming compounds such as this. And lastly, I will also introduce you the organic compounds, but this is just an introduction. The more detailed discussion will be on the next lessons. And with that, I'd like to have a recap of today's lesson. So, for today, we learned how the idea of atoms developed. People have wondered about tiny building blocks of matter since Democritus. But it's John Dalton who gave the first real evidence that atoms exist and combine in simple ratios to form compounds. So what is an atom? It is the smallest unit of matter that makes up everything around us. And in Dalton's atomic theory, he explained that atoms can be broken down further, but at that time, and always combine in fixed ratios. So next week, and I already showed you a while ago, we know that atom is not really the smallest of smallest content of an element. There is also the nucleus, the protons, neutrons, and electrons. And then we also learned how the idea of atoms developed. So we learned what an element is. Elements are pure substances made of only one type of atom, while compounds are made when different atoms bond together, like water and carbon dioxide. And elements are arranged in the periodic table. So periodic table organizes elements to help predict their properties and behavior. So that ends our lesson for today. If you have any questions, feel free to ask me. But if there's none, see you in the next class. Thank you.